Good afternoon. Good morning, everyone. My name is Xinfeng Wang, a PhD candidate at the University of Yamanashi. So the paper I want to show today is KaiJack, contextualized and debiased recommender model. So as we all know, the recommender system has become inevitable daily applications to address information overload, including book, movie, and product recommendations. So the goal of the task is to find out the items that the users might be of interest given the user's historical interactions. And recently, the graph neural network has become state-of-the-art method. They regard each user and item as a node in the graph, and then assess the similarity between node and the accessibility for the targeted node to make a recommendation. However, they still suffer from two issues. And the first one is the over-smoothing issues and the skewed distribution of interaction due to popularity and user individual bias. So what is the over-smoothing issues? It means the over-smoothing node embeddings, which is caused by the message passing through only the connectivities between nodes. So before GCN, we always initialize the feature vectors of node, for example, N1, N2, and N3. And then we always use the GCN to propagate its information to its neighbors. And as we can see, after several GCNs, the features of each node will propagate all over the graph and making plenty of the node having similar information and became indistinguishable. And one of the reasons is that they can only capture the connectivities between the nodes, but they cannot capture the sequential dependencies of neighbors. For example, if a user complete reading a book, and it is quite natural to recommend its sequel. So if N1 is original book and N2 is its sequel, so it should be more contextual relations between N1 and N2 over a random neighbor N3. So this is the smoothing issue and one of the reasons caused to this. And then I'll explain the popularity and the user individual biases. The popularity bias has been widely studied because it makes models recommend popular items over users' real preferences, even though these items, users do not like these items. Well, for the user individual bias, as we all know, even for the same items, different users could have diverse opinions, which makes it more difficult to identify the distribution of item real semantics. For example, the purple color shows the distribution of item semantics, and optimistic users always give an over high reading score, while serious users always leave critical reviews and low reading scores. So there exists the individual bias here, and it will make it more difficult to identify the distribution of the real semantics of items. So to solve these issues, we propose solutions. For the over-smoothing issue, we propose a novel hypergraph convolution operator that learns both structural and sequential contexts to improve the message passing of GNN. And for the bias issues, in addition to the popularity bias, we also model user individual bias to recommend the items. And also we find the imbalanced gradient for updating item embeddings also makes the popularity worse, and we improve the gradients. So this is based on this, we propose the contextualized and debiased recommender model. As we can see in the left figure, the input is the user's historical interactions, and the output is the probability distributions of candidates. And there are two important parts in this model, which are contextualized representation learning and debiased representation learning. So I will introduce this part in more detail. In the contextualized representation learning, we have a novel hypergraph convolution operator. At first, I'll explain there is a strong relation between transformer and hypergraph convolution, in the sense that they both aggregate information based on two relation metrics of the same size. For example, for the hypergraph convolution operator, we have a sub-adjacency matrix, which is A hat. It is L times L matrix. And for the transformer, we have a self-attention matrix, which is Q times transpose of K. It is also L times L matrix. So So we can see that these two metrics represent the different relations of the same node, because L is the number of the user's interactions. So based on this, we can inject the self-attention correlations as a learnable perturbation on the edge A hat into the convolution operator. Here, the perturbation can represent the sequential relations among nodes. For example, in this formulation, we can see the QKV is the same in the transformer, and we can regard the self-attention correlations as a perturbation delta, and we add it to the edge to propagate this information. So in this case, this hypergraph convolution can propagate information by considering both the sequential correlations and also the structural correlations. And it is the same in these figures. Given the input, we can get the QKV matrix, we get the self-attention matrix here, which is L times L matrix, and given the adjacency matrix, we can get the sub-adjacency matrix. After that, we can aggregate the sequential context and the structure context to propagate the information, and finally get the output of the hypergraph convolution operator. And then I'll explain the device-dependent model. We propose the interaction disentanglement, in which we have three important parts, which is item popularity, the item semantic, and semantic embedding, and the user individual biases. At first, we regard the user individual bias as a perturbation to the real item semantics. As you can see here, the per means the item's real semantic, and the delta is the user individual bias. So in these cases, the item semantic embedding can be free from user individual bias, because when we compute the rating scores, we only compute the user embeddings and the item real semantics. We do not take into account this one, but during training, we will consider it. And then the second step is do the popularity debiasing. As we can see, the final rating score is here. During training, we take into account the popularity, but during testing, we will not consider it, because the observed interactions has already been influenced by the popularity bias. So during training, we can take into account this, but during testing, we will not consider it. Here, the popularity embedding is obtained through the positional encoder. This is to ensure that the items of the similar popularity will closely located in the semantic space. And then we also performed embedding leveled popularity debiasing. As the figure A shows the well-trained item embeddings on EAP 2018 dataset, and the red part means the popularity, the embedding of popular items, and the left part means the unpopular items. As you can see, the variance of the popular items are larger than those of unpopular ones. So which means the inner product of any user and popular items is more likely than be larger than those of unpopular ones. This will make the models predict only the popular items over users' real preferences. And so in this case, we propose a regularization terms here. And the figure C shows how it works. As you can see, the black circle means the item embeddings, and the balloon circle means the optimal area for the training set, but it is also overfitting to the popularity. So the rating score, as in the green arrow, it can make sure that the item embeddings run in the correct direction, but and also the regularization terms will pull it a little back every time and reduce the complexity of item embeddings, and finally make like this. As you can see, the variance gap between the popular items and unpopular items is significantly reduced, and this can improve the performance. Then I'll explain the experiment. We conducted the experiment based on 4 public datasets, and we compared 15 baselines for comparison, which are GCM-based, self-attention-based, diffusion-based, and debiasing-based, and over-smoothing elevation-based methods. And this is also over our performance. As you can see, the Bolden font shows the best result, and the underline shows the second best result. As you can see, the proposed model exceeds all the baselines. And we conducted application studies to see which modules are effective. We have two main findings, as we can see in this table. So without ER means embedding regularization. As you can see, it contributes most to the performance, and without SA means without self-attention in the hypergraph convolution. So as you can see, the hypergraph convolution, by taking into account both the sequential and the structural contexts, can improve the performance. And without DIS means without interaction disentanglement. As you can see, also you can see that the interaction disentanglement brings more improvement than incorporating self-attention into hypergraph convolution. And also, it is interesting to know which debiasing categories are effective. Here, the POP means the popularity debiasing, and the IMDI means the user's individual debiasing. As you can see in the red part, the popularity debiasing works better on the Foursquare and the Domain Book dataset, while for the user individual biasing, we can see it works better on the EAP and the movie lens dataset. Also, both the popularity and the user individual debiasing contributed to the performance. And we visualized the limitations of users, items and the users. The upper four figures shows the distribution of item representations, and the downside four figures shows the distributions of user representations. Here, the similar users are close to each other, and the items, the items in the same color means these items have interacted with by the same user, and the users in the same color means these users visited the same item. So as we can see, the proposed model can effectively differentiate the similar users and items through learning the contextualized and the debiased representation from their interactions. And finally, I'll make a conclusion. We propose a KJAC framework to solve the smooth issues in GNN and the skewed distribution of interactions, in which we have a novel hypergraph convolution that can learn both structural and sequential contexts to improve the message passing in GNN. And also we use the interaction disentanglement to mitigate the influence of popularity and user individual biases. And in the future, we will explore more effective ways to balance the gradients to improve the for updating item embeddings, and we will extend our model to automatically exclude the inactive contexts such as sequential contexts on the movie lens dataset. And also, we have released our source code and the data. And thank you for listening.